as a verb, which usually indicates a relationship between two entities. Okay? And we have this co-reference resolution, right? So here it says Khan. We know who that is. But here there is a he had one daughter. So who is this he? For us, it's obvious who he is. But for a parser, it may not be obvious. So who does he refer to? So in this case, we want to resolve this reference. Okay? So we want to say that this he is the same as Khan. In fact, when I was trying to kind of find an example, I originally had Gandhiji as my example. And the sentence was, Gandhi had a son named Harilal. He was born in 1889. So what do you understand from this sentence, right? So the he, Harilal was born in 1889, but the parser did not recognize that. It's true, you can go try it. This is from the Stanford NLP demo that I tried that example. It did not recognize this. So then I had to change the example. So basically what the parser here is doing is it's giving you part of speech tagging. It's saying this is a, I don't know if you can see from the back. So this is a noun phrase, this is a verb, a preposition, noun, noun phrase, things like that. So the various parts of speech are being tagged. And it's recognizing certain named entities like person, right? Person. It's recognized a number, okay? And there is a co-reference resolution part. So there is a mention here of Khan. And this his, right? His is also, needs to be resolved. His means, who is this his? It's Khan's. So that is resolved, it's linked. And again, it's linked all the way to he. So the co-references have been resolved. And then there is the dependencies among the various components of the sentence. So dependency parsing, it's an expensive thing. But you often need it when you want to do information extraction. Unless it's the most simple of sentences, you often need this dependency parsing. So basically what it says is that Khan is the subject, and cousin Nahid is an object of that sentence. So this kind of gels with what we know about RDF, right? So there is a subject and object and a predicate which connects them. So you kind of make use of the parsing, the dependency parsing, to extract these triples that we want. Pardon?
Isn't the dependency part exactly what you want?
Try it with a more complicated sentence and you'll see. Okay? Even this, I think you need a bunch of heuristics to crisply identify that the triple that you want is Khan married Nahid, because it doesn't directly say that Nahid is the object. It says here the cousin and Nahid, they're somehow together, and cousin is the object. So you need a bunch of heuristics to actually figure out, even in this really, really simple sentence. And I did struggle to find a real simple sentence, because in Wikipedia, this was not the sentence that was there. I wanted a realistic sentence for this, but whatever Wikipedia had, there was no way the parsing, you could interpret it properly, okay? So even in this simple sentence, it's not so easy. You need a lot of heuristics. And often I think parsing is the thing that lets these information extraction techniques down, okay? So these are things that you can try out for yourself and convince yourselves, is it good, is it bad? You can go out and try it. Okay, so this was like the background for what comes next. But what I'm actually going to start out with is really, really old. It's 20 years old. It's called Hurst patterns, after the person who proposed it, Marty Hurst. So she proposed this technique for extracting either or this type relationships from text, okay? She proposed this nearly 20 years ago. I think it was 1992, Hurst patterns. And it's quite, I think it was very cool. Whether it works or not on a large scale, that's a different issue, of course. So the point of this is that we want to extract things like Kevin Spacey type Academy Award-winning actor, because Kevin Spacey is an Academy Award-winning actor, and LA is a big city, things like that. So we want to extract these. So what she proposed is to look for a bunch of patterns. So these are the Hurst patterns, and they look something like this, okay? So NP stands for noun phrase, and such as, that's an actual literal that you have to match in the sentence. And then there has to be another noun phrase, and followed by 0 or more comma noun phrase. Okay, so this is a pattern. So you have a lot of sentences, you do part of speech tagging, right? And you look at noun phrases, match literally such as, noun phrase again, and 0 or more noun phrases. So these are a bunch of patterns that she observed in text would usually lead to this kind of relationship. Okay? So what I did is I tried it. I tried it on the web. And what I did was I tried it. So this is for any general object, right? What I did was I froze this part of it. So noun phrase, I have a very specific noun phrase because I want to find out all about Academy Award winning actors. So I freeze this and then see if it works. So here is the phrase query that I gave, Academy Award winning actors such as. Okay? So here are a bunch of results that I found from the web. Okay, a phrase query like this says Academy Award winning actors such as George C. Scott, Warren Beatty, Shirley MacLaine. So immediately you have it. You have a bunch of actors who are all Academy Award winners. And there are your triples for your knowledge base. Okay? Same thing here. I have worked with Academy Award winning actors such as Jennifer Lawrence, Malcolm McDowell, Cuba Gooding Jr. Again, a bunch of people who are all Academy Award winners. You can put it in your database. Right? So what basically this means is that you get this sentence out. This is a candidate sentence. You do your part of speech tagging, and you do a matching, right? So with those patterns, and then you're done. So here's another example, and other big cities. So here I would find big cities, obviously. So again, footprint of LA and other big cities. So LA is your candidate right there. LA is a big city. And then you have Philadelphia and other big cities. So Philadelphia, LA, Paris and other big cities. So LA and Paris, again, into your knowledge base. So this is pretty effective, but how accurate is it going to be? I think you would need to do some experimenting to determine this. So the examples that I gave you just now are all positive examples, and I really handpicked the examples which work, right? But just try giving these phrases on the web. You will find a lot of junk, and separating the junk from the real stuff that you want, that's non-trivial. Okay? So I'd say it works for a certain extent. How accurate it is, I would encourage you to go experiment on your own to see this. Okay, so this is pretty good for the type relationship, right? But type relationship is not the only kind of thing that we want. We want a lot of other kinds of relationships. There are many, many relationships, right? So let's look at an example of another relationship, and I'll build on this example subsequently. So suppose we wanted to identify triples for the relationship has-child. Okay? So we want triples of this form. So Rajiv Gandhi, child of Indira Gandhi, Abhishek Bachchan, child of Amitabh Bachchan, and so on. So we have this corpus, which might be the web or any other corpus, and we want to extract all triples of this form. Okay? So how do we go about doing this? So a couple of options again. We can follow the methodology before. So Hearst patterns basically enumerate the different kinds of patterns to search for, right? So one thing we could do is we could enumerate all these different patterns. So we have a pattern database now, and then go ahead and start searching your corpus. Okay, and you get a whole bunch of candidates, and hopefully you're accurate with it, you don't get any junk, and you're done. But of course, the problem with doing anything yourself is that you don't scale. It's the computer that scales. I mean, you need lots of machines to scale. So enumeration by hand is not going to be a solution if you're really looking to build large knowledge bases. Even for a simple relationship like child of, there is no way one human being can enumerate all the different patterns. Okay? So what we usually go for is to learn the patterns, and I'll show you in a minute how we do that. So here are a bunch of example patterns. So if you have something like X comma Y's eldest son, then you could extract X is child of Y, right? So you have a sentence, and you match this pattern like apostrophe S. So there is a noun phrase apostrophe S eldest son, blah, blah, blah. You can, if you match that pattern somewhere, then you probably extract this relationship from there, right? Similarly, M's son N. So you infer that N is the child of M. And you have something a little more complicated, like A and B had their first child whom they named C. And then you can extract two kinds of, two triples from that. So C is child of A as well as B, okay? But you can see that thinking of these kinds of patterns, one person would never be able to do it, okay? So we need to learn. So let's see how we can do that. So this is one approach to doing this. So what we are given with, to begin with, we have a bunch of example pairs which we know have this relationship child of, okay? So we have example pairs. So we know that Rajiv Gandhi is the son of Indira Gandhi, Abhishek Bachchan is the son of Amitabh Bachchan, and so on. So these are pairs, and we know that this pair of entities are in this particular relationship. So we have examples. Now, what we want to do is to learn the patterns that we should look for in a corpus of documents that we are given, okay? So what we do first is we search the corpus. So this is just this could be as simple as string matching. So you have the term Rajiv Gandhi, you just look exactly for Rajiv Gandhi in your corpus. You have Indira Gandhi, you look for Indira Gandhi in your corpus, straight string matching. Or it could be a little more sophisticated than that. So it could be something like Indira Ji. That could be a reference to Indira Gandhi, right? So maybe you do something more sophisticated than just string matching. You do this entity resolution, it's called. So Indira Ji and Indira Gandhi both refer to the same person. So you find, so the point is that you find these entity pairs in your corpus first, okay? And you look for sentences. So here I'm just saying sentences, but basically they have to be very near each other, because that's when you think that they're going to be in this, analyzing the pattern is going to lead you to an interesting occurrence. So for example here, again I tried this on the web. So Rajiv Gandhi and Indira Gandhi, sorry, Rahul Gandhi and Sonia Gandhi, I'm sorry. It's not Rajiv and Indira. Yeah, probably because I couldn't find examples, but this one I did. So Rahul Gandhi and Sonia Gandhi, I gave these as phrases, and here are some results. So it says here Rahul Gandhi is grandson of former Prime Minister Indira Gandhi, son of former Prime Minister Rajiv Gandhi and Sonia Gandhi, etc. And then the second one says Rahul Gandhi on Monday along with his mother Sonia Gandhi, blah, blah, blah. And the third one says Rahul Gandhi was born in Delhi, the first amongst two children of Rajiv Gandhi, former Prime Minister of India, and Sonia Gandhi. Okay, so just querying these pairs, it gave me a bunch of sentences like this. Now what I need to do is to analyze the text in between these two entities. Okay, so those are potential candidates for patterns that I need to actually search for. So here, for example, this is actually the simplest example which kind of makes sense. So Rahul Gandhi on Monday along with his mother Sonia Gandhi. So just replace Rahul Gandhi with anyone else, search for this pattern and someone else, then you can be pretty sure that these two are in a has-child relationship, right? So this pattern here, so noun phrase, on Monday along with his mother, noun phrase. If you look for that pattern, you have a has-child relationship there. So that's kind of the intuition, or that's the basic idea which we are using here. But as you can see from just these three examples, it's not the greatest thing ever. So how do you, this pattern here, for example, the first one. So noun phrase, is grandson of former Prime Minister Indira Gandhi, son of former Prime Minister Rajiv Gandhi, and noun phrase. That pattern seems to be, it probably doesn't lead anywhere except to find the same sentence over and over again, because it's like too specific, right? So there's only one, like, I don't know, maybe it works for maybe one other pair who's also a grandson of Indira Gandhi and son of former Prime Minister Rajiv Gandhi, but we know that there is no such person. So it works for only one pair here. So this pattern, even if you extract it, is not going to lead you anywhere. And another strong assumption that we are making in this case is that we are saying that Rahul and Sonia, they are related by only one relationship. And that is not the case. So the relationship could be that Sonia Gandhi is the president of the Congress party, and Rahul Gandhi is on his way to becoming president, right? So the sentence could be something like Congress President Sonia Gandhi along with, I don't know, is it the executive, whatever, or leader of the youth league, whatever he is right now, I don't know. He keeps changing all the time. So these two went to Uttarakhand, okay? And yeah, they occur very close together, but the pattern in between these two entities, they are not in a has-child relationship at all. It's saying something else that we totally don't want. Okay, so there is a pretty strong assumption that we're making that the example pairs that we give are in only one kind of relationship. So what do we do if they're not in just one kind of relationship? What if they're in many relationships? So these are some of the issues that we would need to address in real life. Okay? So it's just repeating what I just said. So you have something like these patterns. Maybe this makes sense. This makes certainly more sense than this. That's what I feel. And in fact, for this pattern, I mean, I tried it. I didn't find a single new result. That's for sure. Okay? So there are a bunch of heuristics that people use, to kind of identify the right patterns or pattern candidates at this stage. So these are potential patterns. They're not yet, you're not saying these are the patterns, they're potential patterns. There are a bunch of heuristics that people use. I would recommend that you go back and read about them. So some things that we can do to make these patterns better is, and these are really simple things. So just remove the stop words that are there. Consider the words as a bag of words rather than a sequence of words. So whenever you're doing this pattern matching, you're not matching the sequence exactly. You're just seeing if the words in your candidate sentence and the words in your pattern, they are close, I mean, they overlap quite a lot. And then you say, yeah, this is close enough that I consider this sentence to have the relationship that I want. Okay? So something like this. So you have grandson, former prime minister. I just simplified it from the previous thing. And here you have something like X, mother, Y. So instead of a sequence of words, you're just going to see if mother occurs between two noun phrases. And then you have to have additional constraints like, yeah, I want these two phrases to be within 5 or within 6 words of each other. And then I find mother in between. Then I kind of believe that, yeah, they're in this has-child relationship. Okay? And the other thing is to use, the frequency of the occurrence of the pattern. So one thing you can definitely do is that this pattern here, this ridiculous pattern, you're going to find it for only one entity pair. You search your corpus, but we have several examples here, right? We had so many other examples. Not one of the other examples is going to find this pattern at all. So this pattern occurs with the frequency of 1. You just discard it. On the other hand, this one, maybe if we remove this on Monday, so if it is like X along with his mother Y, along with his mother Y, I would expect that pattern to be a lot more frequent. And given that you have so many examples, you get this pattern again and again and again. So you have a support for the pattern and you say, yeah, this pattern I think highly likely indicates the presence of this relationship. And then you go and search your corpus for this pattern along with his mother, parse it, find the noun phrases, and then say this is a candidate triple for my knowledge base. Okay? Okay. So far what we did we looked at Hurst patterns, which was specific to one type of relationship, so that is a type relationship. And we see that we cannot really generalize it because the number of relationship types that we want to extract are really huge. Okay? So, and I gave you one technique that you could use to actually, so you have a relationship in mind, you come up with a bunch of example pairs, and then you search for these pairs, analyze the patterns in between, and that's how you learn the patterns for this particular relationship. That's one. But again, the thing is, with this kind of approach, you are still limiting yourself to one relationship. Okay? So this relationship, you could be exhaustive. You could find all parent and child pairs. You could find all has-child triples with this technique. But has-child is not the only relationship. Again, there is a problem of scale. You want all relationships, right? So how do we do that? So there's one, I won't say it's new, it's really 5 years old technique called open information extraction. Here what they said is, there is no exact match, there is only meta, right? So for example, this first example here says E1, which is entity. E stands for entity or a named entity. It could be a noun phrase followed by a verb, followed by another noun phrase. That's going to be a relation. Okay? So and the example that they're given here is X established Y. So it could be the founder of a company expressed as, Narayan Murthy established Infosys. That could be somewhere in a sentence. And the way you acquire this is to notice that there is a noun phrase, and there is a verb, and there is another noun phrase. And you just extract them and put them in triple form. Okay? So here's another example. E1, 2. 2 is there is a verb next, and then another entity. Okay? So the example is X plans to acquire Y. So acquire is the verb that's there. And wherever you find these kinds of patterns, it does not need to be acquire, it can be any other thing there as long as it's a verb. You match this meta pattern and you extract it out, and there's another triple for you. Okay? So they kind of generalize this notion of which relationship it should be. It's like it can be any relationship, and this relationship is usually based on the verb that is present in between these two noun phrases. So I guess really distilling that, it comes down to that. Okay? So they have a system online, it's called Reverb. This is from Washington. And you can actually go and see the online demo, and the data for this is also available for download. Okay? So I think this screenshot is not so clear. I tried looking at some of the facts that they have. So for example, this page is all about what kind of crop is grown in which country or which location. Okay? So the kind of relationship that you want to find here is that you want to say that grapes are grown in England, black pepper grown in Mexico. Okay? So the grown in relation, and they have all these relations that they extracted through their technique. Okay? So note that they didn't search specifically for grown in, they just searched for verb. So noun phrase, verb, in, noun phrase. Okay? And then they filter it out with the word grown. So it would be a lot of different triples that were there, and then you do a simple word search for grown, and you come up with these set of, these are tuples which are in that relationship, grown in. Okay? There are also some things which are not so great here. So for example, this one, fruit, India. I mean, come on. Fruit is grown in India. That's not really useful for me, but the others are really good. So now let me show you some things that are not so good. Same reverb. These are some examples from their website, example extractions. I believe they're looking at a health issue-based text somewhere, and they extracted this stuff. So a bunch of things can go wrong. So for example, these first two triples that were extracted, I feel at least, are completely useless. So they don't really say anything. I mean, vitamin C might be an important one that doesn't even make sense. If you read it, it doesn't make sense. Vitamin D has become a focus of renewed interest. Yeah, it may be interesting, but if I knew focus of whose renewed interest and when and why and things like that. So these triples are not really, are not really the kind of thing that I would want in a knowledge base, let's say. Vitamin D retails for $69.95. Well, if I knew when this was the case and I was looking for the cost of vitamin D, I might find it useful, but without the time and maybe the location where it is sold, not really useful. Okay? And another problem here is vitamin C helps in tissue repairs and growth. So it's a nice thing that they extracted this entire thing, tissue repairs and growth, as one thing. But in my knowledge base, if I want it to be crisp, I would want these to be in two separate triples. One would be vitamin C helps in tissue repairs, and another would be vitamin C helps in growth. Growth of what? That's different. But basically, it's an easy thing here because they just extracted the noun phrase that was there. And yeah, I would say it kind of makes sense, but not completely. It could have been crisper than what it is. Okay? And compare these two relationships, right? So vitamin C helps in something, folic acid can help in something. So the problem here is that these two relationships, they mean the same thing, but they're expressed in a different form. Okay, and that's a problem. Ideally, what we want is for both entities as well as relationships to have some sort of canonical form, because that is what makes querying easier. So there's like a uniform terminology, right? Without that, it's just an impossible thing. I mean, this helps in, can help in, will help. So there are like a million different ways you can express helps in. And suppose you are looking for things that can help with your anxiety. How do you even go about querying the knowledge base if the terminology is all over the place, right? So the ideal thing is for, I mean, it should be a required thing that these should have canonical forms, which the raw reverb extractions do not really do. Okay, so these are just some of the issues. These are hard issues. These are not easy things to solve. And people are looking at these kinds of things, especially things like how do you identify that two surface patterns, this is what we call them. So helps in and can help, right? They occur in text. So they're surface patterns. Now I want to convert it into a canonical form. Same thing for these. I mean, you don't see examples here, but I gave you the example of Indira Gandhi and Indira Ji. Yeah, both of them can be there in your knowledge base, but you also want to identify the fact that these two are the same person, right? So there is one canonical form which refers to this entity. Okay? Yeah, and one thing about these useless triples, right? So I was just thinking in the morning, Twitter. Suppose you wanted to do entity extraction over Twitter. What kind of useful things do you think you would get out of it? And how would you recognize whether something is useful or useless, right? Yeah, just something to think about. So you have tweets like, I am watching TV right now. Sure, you can extract a triple out of that, but who does it help? Maybe his friends or, who watches TV in the middle of the day, right? Or his parents maybe. Okay, so we saw information extraction from text, and we saw how we could harvest information from semi-structured sources on the web. So the last thing I wanted to talk about is the sweatshop, which is human computing. So I wonder how many of you are familiar with this games with a purpose? Anyone? Yeah. So this is a classic example of human computing. So it's like you play a game, you enjoy the game, but secretly, you're also helping build a knowledge base, right? So it's like kids. They think they're getting some big reward, but actually they're just doing what you want them. You give them a little bit of candy and say, yeah, I'll give you candy, but you should go to bed, right? So you actually want them to go to bed but they don't realize it because they got the candy. So it's something like that. So you really enjoy playing these games, but in the background, there's a lot of information being collected from these games, which are useful. So here's a screenshot. So there's a website called gwap.com. And after you see this game, don't start playing it, okay? We are not done with the talk. These are, I mean, I tried some of these games. They're really, really fun and interesting. And here is a screenshot of a game called Verbosity. So the way this works is there are a lot of people online playing the game at the same time, and you're partnered with someone that you don't